Good system design is the foundation of a successful central heat pump water heating system. If a heat pump water heater is designed and sized like a traditional gas boiler, the building owner will end up with functional problems and poor performance. So, what does good design look like? It starts with choosing the right system configuration. That choice depends on several factors: the type of heat pump technology used, how water is circulated through the building, and how water temperature is maintained when hot water demand is low. In the US, two main categories of heat pump water heaters are sold today: single-pass and multi-pass systems. In a single-pass system, incoming cold water is fully heated in just one pass through the heat pump. These systems recover faster, which means they require less storage capacity. They also operate at higher temperatures, which improves control of Legionella bacteria. And because many single-pass systems use CO2 refrigerant, the lowest global warming potential refrigerant available, they're an environmentally friendly choice. It's no surprise that most heat pump water heaters on the market today are single-pass. In fact, all the publicly available design tools for sizing currently only support single-pass designs. On the other hand, multi-pass systems work by circulating water through the heat pump multiple times, adding a smaller temperature lift with each pass. These designs need more storage and more careful controls. A subcategory of multi-pass systems is the unitary heat pump water heater, where the heat pump and storage tank are combined into a single unit. These are common in residential applications, but larger versions are available for food service and grocery facilities. In short, while both technologies have their place, single-pass systems often deliver the best efficiency, the least storage requirement, and the most reliable performance in commercial and multifamily projects. Central heat pump water heating systems must serve two main loads: the primary heating load and the temperature maintenance LOA, or recirculation loop loss. The primary load is simple. It heats cold city water up to the domestic hot water temperature needed at faucets and showers. The temperature maintenance load is more subtle. As hot water circulates through the building, it loses heat in the piping. That returning water needs reheating to make sure occupants don't get lukewarm water. How we handle that returning water defines the system configuration. 1. A return to primary system where the return water feeds directly into a multi-pass heat pump system. Or 2. A temperature maintenance system where a single-pass heat pump generates hot water from incoming supply, while a separate temperature maintenance system maintains the water temperature in the circulating loop. Dedicated temperature maintenance systems. These are most common with single-pass heat pump water heaters, since they work best when heating cold water. To avoid mixing warm return water into the primary tank, we use separate equipment: a dedicated tank and sometimes a dedicated heater. There are two main designs. The first is the swing tank. Here, an unstratified tank is placed in series with the primary storage tank. During high water use, overheated water from primary storage flows through and passively heats the swing tank. During low use, the swing tank cools, and a backup electric resistance element kicks in. The second is the parallel loop tank. This design uses a separate multi-pass heat pump to reheat the recirculation loop. It allows primary storage to run at lower temperatures for higher efficiency, but it requires more heat pump capacity and cost. Parallel loop systems are often used when recirculation losses are high, but hot water usage is relatively low. Return to primary systems. Instead of using separate equipment, return water is directed into the primary system. In a multi-pass return to primary system, piping looks very similar to a gas boiler setup, which makes it familiar. But it comes with drawbacks: higher equipment capacity, slower recovery, and lower efficiency. In contrast, single-pass return to primary systems can work efficiently if the heat pumps are designed for it. They must handle return water at around 115 degrees, and controls must be carefully tuned. Manufacturers like Colmac and Nile have models specifically designed for this configuration. No recirculation systems. In some buildings, if the fixtures are close enough to the water heating plant, you don't need a domestic hot water recirculation loop at all. This is the simplest, most efficient design. It eliminates return water issues and pumping energy. It's especially effective with single-pass and integrated heat pump water heaters. Integrated heat pump water heaters. These unitary systems combine a heat pump and a storage tank into one appliance. They're usually multi-pass systems and work well in residential, food service, and grocery applications. But in multifamily buildings with high circulation loads, the onboard electric resistance heaters fire too often, lowering efficiency. For that reason, they're best used where there is no circulation loop. Finally, stratification is critical for single-pass heat pump water heaters. Cold water needs to stay at the bottom of the tank, while hot water is stored at the top. This layering allows the system to operate efficiently with a large temperature lift. If warm return water mixes in and destratifies the tank, efficiency drops sharply. That's why maintaining stratification is a core part of system design. In summary, single-pass HPWHs paired with dedicated temperature maintenance systems deliver the best efficiency. Swing tanks are simple and cost-effective, while parallel loop systems are better for high recirculation losses. Return to primary systems are familiar but less efficient, especially in multi-pass setups. No recirculation is the most efficient option when possible. Integrated systems are best for residential and small-scale applications, and always protect stratification for stable operation. Good design decisions here make the difference between a high-performing CHPWH system and one that struggles to meet demand. When designing central heat pump water heating systems, the choice of refrigerant is critical. It affects the temperatures the system can deliver, how it performs in different climates, and even the environmental impact of the installation. Let's look at the three most common refrigerants used in HPWH systems today: R134A, R410A, and R744, also known as CO2. R134A systems can heat water up to about 160 degrees Fahrenheit, but they struggle in cooler conditions. Below 60 degrees ambient, capacity drops sharply, and below 40 degrees, performance becomes extremely poor. Because of this, R134A equipment is best for warm or mild climates. In cooler regions, it can sometimes be installed in protected spaces like below-grade parking garages, but it is not suited for true cold climates. R410A can operate in very low ambient temperatures, down to 0 degrees Fahrenheit. That makes it attractive for colder climates. However, it can usually only deliver hot water up to about 125 degrees, and when outdoor air drops below 40 degrees, even that can be difficult. To reach higher delivery temperatures, R410A systems often need a booster or trim tank to finish the job. R744, or CO2, is different. It can provide extremely high water temperatures, up to 180 degrees or more, and it performs well even in freezing conditions below zero. The trade-off is that CO2 must run at very high pressures, which requires strong, reliable piping and shorter distances between the compressor and the condenser. But from a climate perspective, CO2 is the clear winner. It has the lowest global warming potential of any refrigerant used in HPWH technology today. Beyond performance, refrigerants are also a regulatory issue. Both R134A and R410A are scheduled for phase-out under the Kigali Amendment by 2035, and states like California are moving even faster. Manufacturers are testing replacements like R32 and R11234YF, but it's not clear if these will be drop-in solutions or if they'll require major design changes. That uncertainty makes CO2 the most future-proof option. It's efficient, it's flexible across climates, and it's aligned with long-term environmental goals. When designing a central heat pump water heating system, equipment layout is just as important as system design. The way you locate compressors, storage tanks, and supporting components can make the difference between smooth operation and long-term headaches. Locating heat pump. Most HPs are installed outdoors, But in cooler climates, parking garages can be an excellent option. For example, studies in Seattle showed that garage installations kept inlet air above 50 degrees year-round, even when outdoor temperatures dropped much lower. When placing heat pump in garages, it's best to exhaust the air directly outside or interlock the garage exhaust fan so that the heat pump exhaust is captured. There are several rules of thumb to follow for outdoor placement. Maintain clearances for service access and airflow. Keep units perpendicular to prevailing winds. Avoid placing them near windows or roof edges where noise and runoff can be an issue. Ensure proper condensate drainage and prevent discharge air from blowing into nearby units. In cold climates, elevate above snow levels and, if possible, install them in semi-protected alcoves. Locating thermal storage and temperature maintenance systems. Storage tanks in CHPWH systems are often larger than those in conventional systems and may be installed in series or parallel. This means engineers must plan for the size, weight, and seismic requirements of these tanks, especially if they are placed on roofs or slabs. A floor drain is mandatory for condensate and relief valves, and digital thermostatic mixing valves should be specified to maintain consistent delivery temperatures. Mechanical wax-type valves react too slowly to the temperature swings in these systems. The temperature maintenance system is usually located near the storage tanks, and space must be coordinated with plumbing, electrical, and structural requirements. National Electrical Code also requires 3 feet of clearance in front of swing tanks. In some configurations, a secondary heat exchanger is required between the outdoor compressor and the indoor storage tanks, which means more space and additional drainage must be planned for. Retrofit considerations. Retrofitting existing gas or electric water heating systems can be complex. One of the first things to verify is electrical capacity. Gas to electric conversions often need service upgrades, which can be costly if not identified early. Site visits are critical. Both engineers and contractors must assess conditions to locate outdoor or garage space for compressors and indoor space for tanks, recirculation, and other components. Don't overlook acoustics. Placing units too close to tenant windows can lead to noise complaints. Existing storage tanks can sometimes be reused as swing tanks. Old electric resistance tanks are especially useful, and gas-fired tanks can sometimes be repurposed with minor modifications. Perhaps the most important retrofit consideration is limiting disruption to tenants. In many multifamily buildings, interim equipment or temporary hot water service will be necessary during the transition. Planning for this keeps residents comfortable and avoids major complaints. Multifamily. DHWH sizing Ecosizer is an online tool developed by Ecotope Inc. to size central HPWH systems for multifamily projects, available at www.ecosizer.ecotope.com, or you can use manufacturer-provided selection tools or sizing tools. How a DHWHP is sized. What is MEP engineer's responsibilities? 1. Estimate occupancy. 2. SB ASHRAE, daily usage per person. 3. HPWH required recovery, daily usage, desired run hours. 4. Must account for defrost if HP is air source type. 5. Rule of thumb, storage. 20% of daily usage, based off 16 daily run hours. Basic information on the system parameters are required for sizing a system. Source, type, air or water. Water temperatures, cold water supply temp, stored hot water temp, mixed water temp. Building type, office building, multi-use, multifamily, hospital, school, etc. Total daily use. If you don't know, we have tools to help you determine the loads. Ultimately, this is the responsibility of the specifying engineer. Building loop losses, min flow of mixing valve, including GPM and T, BTU HR, GPM 500, TDGF. It's a constant drain on the system and must be made up or absorbed during non-use periods. System-level factors affecting efficiency. 1. Climate and installation conditions. 2. Storage tank size, arrangement, and stratification. 3. How temperature maintenance systems are integrated, recirculation loop looses are addressed in the design. 4. Role of backup systems, e.g., electric resistance heaters. 5. Control strategies, standalone operation or central building management system integration. 6. Building water demand patterns and timing when the peak load occurs. 7. Ratio of primary heating load to recirculation, maintenance load. When designing a domestic heat water system for your building, consider about your SysCop. SysCop accounts for the entire system: the heat pumps, the storage, the temperature maintenance, and the way everything works together. It's calculated by dividing the annual energy delivered as hot water by the annual energy consumed. SysCop gives owners, designers, and policymakers a much clearer picture of real-world performance. That's why programs like the Advanced Water Heating Specification and the California Energy Commission's compliance approaches now evaluate systems based on SysCop rather than just individual equipment ratings. Decide which option to buy. A fully packaged skid is best when schedule, quality control, and a single point of responsibility matter most. It arrives factory assembled and tested, then connects to building water, power, and anchors. A fully specified built-up system mixes vendor components but keeps one provider accountable for the set. It offers flexibility with moderate risk. A custom-engineered plant fits unique sites and complex retrofits, but demands rigorous QA and commissioning. If your team is new to central HPWH, start with a packaged skid or a single vendor built-up approach. Finally, which HPWH to buy for your building or for domestic hot water application. Single-pass units are the efficiency leaders for primary domestic hot water. They love cold city water and work best with tall, stratified vertical storage and a downstream mixing valve. Multi-pass units excel when the hot water circulation loop returns warm water to the plant. They can heat that loop well, though overall efficiency is usually lower than single-pass. Integrated or unitary models package the heat pump with a tank and backup element. They shine on small satellite loads or clusters, typically indoors. For most multifamily centrals, use single-pass for primary heating. And if you need dedicated temperature maintenance, use a small multi-pass unit for the loop.